Hello everyone, thanks to everyone for watching this video. My name is Qida. I am an architect and engineer. Today's video is titled Codeform Steel Structure, and it is going to provide you the fundamentals of codeform steel member and also the mathematical derivation of finite strip method. I am going to give you an overview of what I am covering in today's video. First at all, it is a bit of background to the topic, and then focus on the classic finite strip method and the constrained finite strip method before ramping up with conclusions. Codeform steel structural elements are steel structural products made by bending thin flat sheets of steel at ambient temperature. Codeform steel structures have a history of over a century, and recently, it has become widespread throughout the world thanks to the more economic production of steel coils. Nowadays, codeform steel structures are employed in a wide range of applications, such as roof purlins, stud walls, storage racks, wall and roof cladding, and more recently, even as primary load-bearing members in low and medium-rise buildings. Codeform steel has many advantages, such as a high strength-to-weight ratio and a relatively straightforward and versatile manufacturing process, leading to a high flexibility in the cross-sectional shapes which can be obtained. However, the manufacturing process limits their wall thickness, and as a result, they are susceptible to various instabilities. This may include coupled instabilities, where buckling molds of different types interact with each other, such as local, distortional, and global. In order to gain a deeply understanding of coupled instabilities, it is useful to analyze it using a model decomposition method. In this method, the deformed shape of a buckled codeform steel member is decomposed into a linear combination of individual buckling molds, each with a specific mechanical significance. In doing so, it is possible to study the behavior of each isolated buckling mold, as well as determine their contributions to the overall behavior of the member when coupled instabilities occur. Currently, two basic design methods for codeform steel members are formally available in design specifications in Europe and North America: the traditional effective method and the direct strength method. The essential idea of the effective width method is that local plate buckling leads to reductions in the effectiveness of the plates that comprise a cross-section. The effective width of each flat element of the cross-section has to be determined. As a result, each element is considered separately, ignoring the rotational restraints provided by the adjacent elements. To address this, the direct strength method is proposed. This method is predicted upon the idea that an engineer determines all of the elastic instabilities for the cross-section, and also determines the moment or load that causes the section to yield. Then the strength can be directly determined. The critical stresses used to calculate the slenderness associated with different types of buckling are determined using the signature curve obtained from the finite strip method. The finite strip method can be seen as a specified finite element method, specifically developed to study buckling of prismatic thin-walled structural members. The method differs from the finite element method in that only a cross-sectional discretization is required, leading to the emergence of strips rather than elements. As a result, the number of degrees of freedom involved in the analysis is significantly reduced, thus improving computational efficiency. The strips are separated by nodal lines, which are often simply referred to as nodes. At the very minimum, a cross-section needs to be discretized into a number of flat plate segments connected at main nodes. Although each plate segment can be further discretized into smaller strips at some nodes, main nodes associated with only one strip are termed external main nodes. as opposed to internal main nodes which connect multiple strips. In the finite strip method, a local coordinate system is defined for each strip, as well as one global coordinate system. In the global coordinate system, each of the nodal lines is associated with the following 4 degrees of freedoms. The translations big U in the x direction measured at the specimen ends, which are assumed to be equal and opposite, in addition to the translations big V and big W in the global y and z directions, and the rotation big theta about the x-axis, all measured at mid-length. In the local coordinate system associated with each strip, the corresponding degree of freedom are the translations small u in the x direction measured at the specimen ends, as well as the translations small v and small w in the local y and z directions, and the rotation small theta about the x-axis, all measured at mid-length. In what follows, the displacements u, v, w will also be referred to as the warping, transverse, and out-of-plane displacements respectively. In addition, the displacements small v and small w are often termed cross-sectional displacements. The notations are regarding local and global displacements for a strip with length a and width b. In the finite strip method, the longitudinal shape functions are assumed to be trigonometric. Thus, for a thin-walled member with pinned boundary conditions, the global displacement of the m's nodal line can be expressed, where q is the number of half-waves within the member length a. Ym is the longitudinal shape function. Uim, Vim, and Wim are the amplitudes of the displacement values, and θim is the amplitude of the rotation. The strain displacement relation that defines the strips is a combination of a plane stress condition for the membrane degree of freedom U and V, and a Kirchhoff thin plate theory for the bending degree of freedom W. The strain can be expressed. The strain displacement relation is combined with the shape functions in the conventional manner. First, the internal strain energy can be formed, where D is the matrix representation of the generalized 2D Hooke's law, and B defines the relationship between the strain vector epsilon and the displacement vector D. From the strain energy expression, the local material stiffness matrix small ke can be expressed. This matrix is traditionally broken into membrane, plane stress, and bending terms. Using the strip connectivity, the strip stiffness matrix is assembled into the global stiffness big Ke. The local strip geometric stiffness matrix is formed from the work done by the edge tractions on the second-order strains, and the matrix can be expressed, where T is the distributed traction over the cross-section, epsilon y2 is the second-order strain, and G is a matrix that describes the relationship between the second-order strain components and the displacement vector. From the work expression, the strip's geometric stiffness matrix small kg can be formed. This matrix is also typically expressed in terms of membrane and bending terms. For a given distribution of edge tractions on a member, the geometric stiffness matrix scales linearly, resulting in the classic eigen-buckling problem. In this problem, big lambda is the matrix containing the load factors. Big phi is the matrix containing in its columns the vectors of the linear combination factors, for example, amplitude factors. For the special case of simply supported end conditions, the m longitudinal shape function terms are orthogonal, and thus each m term is separable, and the problem may be approached as a series of q separate solutions. The method was tested on a cold-form steel-lipped channel and a hollow flange cross-section under compression. The mechanical properties of the material were assumed to be Young's modulus E equal to 210,000 megapascal, Poisson's ratio mu equal to 0.3. The classic signature curve for the stability of the thin-walled member results as shown in this slide. However, the buckling modes identified in the signature curve are difficult to know. The constraint finite strip method, CFSM, is an extension to finite strip method that uses mechanical assumptions to constrain Ke and Kg down to those deformations that are consistent with the desired set of criteria. For example, those consistent with local, distortional, and global buckling. The CFSM constraints are defined in the table and are applied to formally categorize deformations into global G, distortional D, local L, and shear, and transverse extension ST deformation spaces. Especially, any FSM displacement field D may be constrained to any deformation space M, where M equal to G, D, L, and ST, via D equal to Rm times Dm. Explicit determination of Rm is lengthy, but not overly complicated. The shape functions are applied with the mechanical criteria of the table to achieve the desired constraint matrices. Modal decomposition of the eigenbuckling solution is completed by introducing the desired constraint matrix Rm that constrain the deformations to the desired space M, and thus the FSM equation becomes a new equation. The new equation reduces the problem size to the size of the M space and constrains the deformations to be consistent with that same M space, effectively decomposing the solution. Modal identification of any FSM solution is also possible. First, we must recognize that G, D, L, ST spans the entire FSM deformation space. As such, taken as a whole, the developed Rm constraint matrices represent an alternative basis in the FSM space, one in which deformations are categorized. This basis transformation of a general displacement vector D can be expressed, where C now provides the deformations within each class, CG, CD, CL, CST. The values of C are dependent on the normalization of the base vectors within R. Here, a simple vector norm is used throughout. This norm provides practically reasonable results. It's most consistent with norms used in general beam theory, GBT, and is most compatible with the application of CFSM in FEM model identification. Once the C is determined, participation in each mode must also be determined. The vector norm is used. The ability is to quantitatively define the participation in a given deformation space, provides a unique measure of coupling amongst the deformations if the deformations are coincident with buckling modes. Then the participations are a direct measure of the degree of coupling in the given instability. The application of modal decomposition and identification on the signature curve analysis of the simply supported lipped channel and the hollow flange channel of the previous figure is provided in this slide. The modal decomposition provides pure mode deformation space solutions. The modal identification is scaled by participation so that the identification may be visualized along with the signature curve. The results indicate how local, distortional, and global couple as a function of buckling, half wavelengths, and further indicate for hollow flange channel distortion buckling participating less. From conclusions, what we learned: the finite strip method is an efficient numerical tool that has provided a unique ability to improve our understanding of thin-walled member stability. The constraint finite strip method extends the compatibility of the finite strip method to include modal identification and modal decomposition. Okay, thanks to everyone for watching my video today. and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.